A particle moves in simple harmonic motion and comes to rest. Might have to think about what that means. When its displacement is 10 on pi meters, as if. Maths textbooks. Like, who measures in 10 on pi? Seriously.
Well, you can't. It's irrational.
I know, right? 10 on pi, go figure. Approximately 3, I guess. All right. The period is 3 seconds, and that's a trick question, amplitude is A meters. Do they really go? Yeah, good, okay. Determine velocity when in equilibrium position. I skipped a few words, so it doesn't quite make grammatical sense, but like you, I don't like writing all those words.
If we start with simple harmonic motion, do we have to start with displacement, or can we go straight to velocity because we know what the derivative is, or like what it would look like?
I would write the displacement and therefore velocity.
Okay, yeah.
Just to be clear. But there's another way to do this one. Because of the information they've given us. Oh, yes. They're going to derive the equation. On the formula sheet, Travis, you got the remote. This formula. So they are telling you this one, period is 2 pi omega. Normal frequency, as opposed to angular frequency is 1 on the period. They give you this, and therefore it must be this or this. But they also give you this one. This one is sometimes the easier one to use. How on earth did they come up with this formula? Well, what do we know? We know that acceleration is negative omega squared x. But we also know from the next line on the formula sheet that acceleration is also the derivative with respect to displacement, which is going to come up in this one, of half v squared. So to do, hopefully correctly, what I think a couple of you tried to do on that last exam and didn't get right, I'm going to integrate both sides with respect to x. So I'm just going to get half v squared on this side, or the a. Now I'm going to get the integral of minus omega squared x dx. Well, omega is a constant, so that means half v squared is so, from this I'm going to end up with that formula. So, v squared is minus omega squared x squared plus some new constant but what else do I know? I also know that simple harmonic motion, think of something on a spring, when it comes to rest, V is 0, it's at either plus or minus amplitude. When it's at equilibrium position, its velocity is at its maximum. There's one more thing you can know about that. When it's at its equilibrium position in the middle, if it's above equilibrium, acceleration is downwards. If it's below equilibrium, acceleration is upwards. So at equilibrium, its acceleration is 0. So you can often use those kinds of things to work out what my constant is. In this case, V is 0. V is 0 when x is amplitude. So 0 equals minus omega squared a squared plus 2c. So therefore, my constant, my double constant, is omega squared a squared. That was an ugly omega. Omega squared a squared. Which means v squared is negative omega squared x squared plus omega squared a squared, or as it says on the formula sheet. Now, I don't think you actually have to be able to get there, but you can. What does the syllabus actually say? It says, consider and solve problems including simple harmonic motion. And they give you this formula on the formula sheet, so I can't imagine they want you to be able to get there. But you can if you need to. Okay. In this specific case, what do I know? The particle comes to rest at this displacement. That means this has to be my amplitude. Here, my amplitude is 10 on pi, because that's where it stops. It stops at the extreme end of its motion. The period is 3 seconds, so omega must be 2 pi over 3. And therefore I can use this equation to go quickly from equilibrium position to velocity. So at equilibrium, well, that's hard to write. I know my displacement is 0. So velocity is 10 on pi squared, right, no, wrong one, omega squared, 2 pi on 3 squared, bracket, a squared, 10 on pi squared minus 0 squared. Got all these beautiful numbers and pi's, so let's avoid the calculator and get an exact answer. Have a go at simplifying that without looking at the example in the book.
Oh, it works out alright.
It does turn into a nice number. It looks a bit scary there. 4 pi squared on 9 times 100 on pi squared.
Both square numbers, yeah.
Yep. Be careful, Shannon. What's wrong with what I'm writing here? What have I forgotten?
Plus or minus.
Plus or minus, you remembered. Good. So velocity is plus or minus 20 on 3 meters per second at equilibrium. And that is its maximum velocity. And that makes sense. If it is doing simple harmonic motion, at the middle it's going the same speed but opposite directions depending which part of the cycle it's in. Maybe I'll say one more thing about simple harmonic motion. I will say this because, famously, there's a question on an external exam about this. There has been. If I get something that's moving in a circle, think like a Ferris wheel. Here's a good example. I've got a Ferris wheel, right? And I've got all these things moving around the circle. Imagine you are here on the Ferris wheel. And the Ferris wheel is turning this direction. The sun is directly above because it happens to be noon. Wasn't that convenient? What's your shadow doing? How can I model what's happening to your shadow? Your shadow goes this way, then that way, then this way, then that way. Can I be more specific? Yes, I can. The shadow's position corresponds to the x-coordinate, the horizontal coordinate, as you move around this circle, which means it corresponds to a cos function, which means your shadow is moving in simple harmonic motion. A linear projection of something moving in a circle is simple harmonic motion.